to everyone.
Yes.
Okay, so we are going to discuss today about life cycle assessment of bioenergy systems. We'll mostly cover the basics and a few applications depending upon the time, how the time goes. So now life cycle assessment has been gaining a lot of popularity in the recent past, maybe last 10 years, and lots of people have been talking about it, what it is, or does it like we can be just, and also it has a lot of accusations as well, like how can we believe the results? Can we believe the results or not? So this class we'll try to understand what life cycle assessment exactly is, what things it can, or what data or what results it can give us, or how nicely we can believe the results, or are there any results that we need to neglect. So these are some of the topics that we are going to discuss and some of its applications to bioenergy systems. So now, as the name suggests, like life cycle assessment, it has two things, which is called life cycle and assessment. So putting it in simple terms, it's assessing the emissions throughout the life cycle of any product or process. Or if I go by the standard definition of life cycle assessment, it would go as follows, like you can see it on your screens. It's compilation and evaluation of the inputs, outputs, and the potential environmental impacts of a product system throughout its life cycle. So the important thing here is the life cycle. We are just not considering one life stage, it's the life cycle. From the birth of the process till its maintenance and the final disposal of the product. Then the important thing is compilation of inputs and outputs. So life cycle would involve compilation or inventorization of all the inputs or all the major inputs and outputs which are related to that product or a process. It would also involve evaluation of that, the different inputs and outputs which are related to the product. Now these inputs and outputs could be at different product stages. Like suppose we grow biomass, a lot of inputs will go into it. You need machinery for sowing or for tilling the soil at the first place. Then you need fertilizers, you need pesticides, you need harvesters. And once the crops are there, you need to separate the crop components. Like in India, like we have a lot of agricultural waste. So the husk needs to be separated, the stalk needs to be separated. And all these events would have certain energy inputs. There might be a lot of manual labor that is going into it, but a lot of energy goes into it. And that energy, where it is coming from, we need to compile that. And also you can see here the word potential environmental impacts. So I'm going to predict you like these are the possible environmental impacts. A lot of these emissions are easy to quantify, but what's not easy to quantify is the effect of those emissions. And that's why the word potential is being said here. The amount of emissions, okay, this is 1 kg of CO2 is going into the atmosphere. This is something we can quantify. But how much global warming this 1 kg of CO2 is going to give to the atmosphere or to the planet Earth is very difficult to quantify. So that's why we always have the potential environmental impacts. We are not pretty sure that this is exactly what is going to happen, but we can be like confident, like the chances are this, like we are going towards this pathway, like the IEA or the COP conferences that we have always predicts about like maintaining the global temperature to around 2 degrees Celsius. Some people say that we have already exceeded and we can't now achieve that target. Some people say there is still chances to achieve that target. So it's always a potential. And also you can see an asterisk here. So this asterisk says that the whole process is guided by ISO guidelines. And it's ISO 14040 to be specific. So most of these guidelines were prepared in conjugation with IPCC and other bodies. So there are very strict guidelines that govern. So if we are trying to do an LCA for our process product, it's important to study these guidelines. Now the whole process is split into different stages and phases. We'll discuss them in more detail in the later part of the presentation. By stages, I mean what are portions of the life cycle. The stages could be growth of biomass, then transportation of biomass. After transportation, you need to do a pre-treatment of biomass, then conversion process itself, post-treatment if there is any requirement, use of that product, and finally disposal. By phases, I mean what are the phase in which LCA is carried out. The first thing is you would need to define a goal and scope, what the goal of your LCA is. Then you need to collect the inventories. Then you need to do an inventory evaluation, and finally interpret the data. The data is collected on inputs and outputs of the system. A lot of data would be required for the different inputs and outputs, and there are different sources. Some of the data is something that would be specific to your process or product, which you need to do it yourself. Some data would be easily available. Say the electricity that you're using is coming from the grid. So you can approach the electricity department and they can give you the information how that electricity is produced. If that electricity is produced from coal, it would have a lot of CO2 emissions associated with it. If the electricity is coming from hydropower, as is like maybe the case of Uttarakhand in India, it would have very less CO2 emissions associated with it. So data collection is associated with LCA. And then we also get associated environmental and resource impacts along with that inputs and the outputs that we are considering. So this is a brief about life cycle assessment. Now let's go through the history of LCA. Now LCA, as we know today, has been through a lot of like additions and subtractions. It started in the late 1960s and 70s when the concepts of energy efficiency were becoming prominent. This is the same time when the pinch analysis was also gaining prominence. Like we all discussed pinch analysis in the morning class. So it owes its start to that point where the energy analysis was getting a lot of prominence. Then by the 1980s, we have the oil crisis and people were talking about how we are going to get the resources in the future. By the 1990s, we had the Kyoto Protocol and greenhouse gases and global warming became much more prominent. And so people put a lot of focus on what all gases are causing that greenhouse gases and if they could be prevented, or at least if there is a matrix in which we can quantify how much greenhouse gases are being caused by which process. And by the coming to the year 2000 or 2005, we had the concept of life cycle assessment, where people thought it's not just the greenhouse gases, we have much more to it. It could have ozone depletion, it could have eutrophication, which means the increase of nutrient quantities in the water bodies. It could have acidification, means increase in acidity of the marine environment or the atmosphere. It could have human health. It could have ionizing potential, which could come from nuclear fuels. It could be agricultural land occupation or land occupation as such. It could be resource allocation or fossil fuel depletion. So life cycle assessment as we know today has come up from a lot of research in different fields. It's not just greenhouse gases as the thrust has been. Like most of the papers that you study around would say life cycle assessment, but the final result that you see is this process is causing this much kg of CO2 equivalent per the functional unit. So is that life cycle assessment all about? Not really. Life cycle assessment has much more to it. It's not just GHG emissions. It has a lot of matrices that are associated with it. Again, just to give you an example of life cycle assessment, like in the year 2007, OECD, which is the Organization of Economic Cooperation and Development, an organization of developed countries of the world, came up with a very nice report. You might want to study it. It says biofuels. Is the curse worse than the disease? So this was the time of around 2005 when biodiesel was gaining a lot of importance, specifically in the US. And they had huge corn fields, they still have, and they were using those corns to produce biodiesel. And the report was about the evaluation of what were the effect of that biodiesel use on the environment. And lo and behold, they found that these processes involved a lot of water use. And this water use could be sometimes 100 times the water that would be required for a normal energy production process. Now, this water use was a critical factor. And see, in a country like India, which has limited water resources, If we are using a lot of water in the growth of biofuels, it could cause major environmental impacts. Another impact that this report came up with the transportation. Now, biofuels also have a good amount of transportation associated with it. There was a study in the year, I believe, 2008, which said like if you transport biomass for more than 100 kilometers, you are basically spending more energy on the transportation than is present in the biomass. No matter what process you use for its conversion, that doesn't make a difference. If you are transporting biomass for more than 100 kilometers, you have already spent more the amount of energy than there is stored in the biomass. So these are the types of things that LCA wants to highlight. Again, it has four major phases, which is called the goal and scope, inventory analysis, impact assessment, and interpretation. We are going to study them in greater depth as we go ahead. So let's come across, like, we are now in 2020. What are the commonly used LCA matrices? Now, this is a normal term that is used to point to the LCA impact categories. It's called matrices because calculation of LCA normally involves matrix algebra. They form large matrices which have all the inventories. So that's why the term matrix is often used. And most of them focus on the energy demand. What is the energy output per the energy input that you're getting? Global warming. We all know about this fact, all the COP21 or like all these have been focusing on global warming. And you also use another term for this global warming, which is called climate change. Now, there's a nice history why they use the term climate change instead of global warming now. Now, global warming has a sort of negative connotation attached to it. It says that something is warming and it might have a bad effect on us. Climate change, on the other hand, is more of a neutral term. It says that something is just changing. It might be a positive thing or a negative thing. We can't say. So people now want to use the term climate change just to say that it's a neutral term. The climate is changing, they agree, and it's warming. They also agree, but they still want to say like the word climate change because they don't want a negative feeling attached to it. So this is how sometimes the choice of words also affect the inference that you get or derive from those words. We also have the ozone depletion. We have ozone holes at different places in the world. And when this ozone layer depletes, you have the UV lights coming in. And if we are exposed to those UV lights, it causes diseases like cancer. We have the water footprint. And this is specifically related to energy use. You might be hearing the term food, energy, water nexus nowadays. So energy and water are closely interrelated. And they are much more interrelated when we are talking about biofuels. So biofuels invariably would need water for the growth of biomass. And this water sometimes can be like few orders of impact, few orders of magnitude higher than what was the water used for fossil fuels. So this is a thing that we need to worry about. Then we have the ecological or the human toxicity. Are the pesticides or the insecticides that might be used, or even fertilizers, the chemical-based fertilizers that go into the production of biomass, might cause toxicity in our natural environment, which might lead to decline in ecology as well as human beings. And then we also have land use. So by land use, I mean like you grow biomass for fuel production at one place. So that might occupy the land which was used for agriculture. Now the agriculture might have to elsewhere. So that means there is a change in the use of land. Or that land might earlier be a forest, which would act as a sequestrator of carbon, but not anymore. It is used to grow biomass. It still sequestrates carbon, but it gets released also. So the carbon is getting into the cycle and getting released also. So it's not a net sequestrator in that case. So the use of land has changed. And this land use would also have emissions associated with it. So I'm just talking about some commonly used LCA matrices that are becoming prominent nowadays so that you get an understanding of where we are heading. So now, what an LCA can do for you? It can highlight the efficiency opportunities. It won't give you how efficient the process is, but it can highlight which are the product stages or the process stages which are causing a lot of emissions, and that might be a cause of concern. They might be the hotspots where you need to bring your attention. It might happen that some things which become prominent might not cause as much emissions as others. Like in the case of transportation of biomass, transportation leads to a lot of emissions, but people hardly give any emphasis to it. It can also help you identify the areas in the value chain that needs improvement. It can ensure that the changes do not shift the burden. So you need to see that the changes that you are proposing doesn't change the burden from one to another thing. Like it might happen that you choose a process which is very efficient in converting biomass or highly efficient, but it also needs a lot of pre-treatment. Say like you are coming up with a process which is becoming now famous, like hydrothermal liquefaction. It can produce biomass in good quantity, or like the energy or crude in good quantity, but it would also need processes like hydrotreating and hydrocracking, which would again consume a lot of energy. It can highlight the trade-offs. Which bioenergy supply chain could be better in terms of CO2 emissions? Again, the same point, compared to systems which deliver the same service. It can help you benchmark the progress. Now, there is a certain standard in the US which says if you're talking about advanced biofuels, it means 60% reduction to the as compared to the conventional biofuels. Conventional fuels. So it is said like a conventional fuel like gasoline would have an emission of 93.1 kg CO2 equivalent per megajoule. So if you want a biofuel to be called an advanced biofuel or something that the market would see as a prospective fuel, it should have emissions throughout its life cycle which are 60% reduced as compared to that value. So it can help you benchmark according to the standards which might be set by the government or the private entities. Again, it will give you the footprinting data and support environmental claims. Now, you might have come across the packaging or saying like this is environment friendly, so and so CO2 reduction. So all those things rely on this LCAs, which would help you quantify your environmental claims. So this is what an LCA can do for you. But there are certain things which LCA wouldn't do for you. And these are things like the product performance. It wouldn't give you the product performance in terms of its quality and quantity. We are not measuring that. It's not going to give you any compliance with the environmental laws. Environmental laws, I mean like you are emitting these emissions or this much. You are bringing in data, but that doesn't mention that it's complying with the environmental laws. Different countries would have different laws, and you need to take care of them separately. It wouldn't give you bricks and mortar of capital equipment. We are not talking about techno-economic analysis or anything like that. We are not bringing economics into this. Again, like there are certain LCAs which are called input output or economic input output LCAs, which have the principle of economics built into it. But for most of the standard LCAs, that wouldn't be a part of the LCA. So we are not talking about any capital expenditure or operating cost when you're talking about the LCAs. Also, it is usual that we would neglect the minor inputs and the minor outputs. Typical industrial process would have like thousands of inputs and outputs. So we just can't quantify each one of them. So it's natural that we would neglect the minor inputs or outputs. Again, it's not a risk assessment analysis. It's just going to give you the figures of the emissions. Now it's up to you or up to the different protocols that you support to calculate if there is a required amount of risk associated with it or not. So these are some things that the LCA wouldn't give you. Now, coming to the different phases and stages of an LCA. Let's start with the phases. It has 4 main phases. So any LCA that you do in the future would have to have these 4 stages. The first one is the goal and scope, which means you need to define what are you intending to do, what your audience is, what is the function unit, what is the system boundary, what are the basic assumptions. To put it straight, what are the assumptions you are undertaking while doing this LCA? The second thing is inventory analysis. You bring in all the inputs and outputs, how much mass or energy is going into each product stage and how much of it is going out. Third thing, you quantify all these inventories into impact assessment. Now I have all these inputs and outputs going at this particular product stage. And if I normalize it throughout the product cycle, this is what my emissions are going to look like. And finally, the interpretation. How do I interpret those results? Now, an interesting thing to note here is all these errors are bidirectional. This is no one directional, which means the whole process is iterative. You just don't start from one place and reach the other phase. You start with one phase, see the output, and then it's fine to go back and update your assumptions, update your inventories, update your impacts, which you are considering, and update your interpretation. So a lot of LCAs would involve to and fro, like hit and trial, getting this output and then trying to make sense of it. And then you see this is where you're making a wrong assumption, go back, correct it. And this is a normal part of LCA. Now coming to the stage, a normal product or process would have these following 4 stages, which would mean there's an extraction or upstream production, then the manufacture or the conversion process, as in the case of bioenergy, the use of those biofuels or bioenergy, and then final disposal or recycling. And in between them, you also have transportation. So the inputs and the outputs that go into all of 4 of this would basically make this inventory analysis. So each LCA would have different phases, which are 4 in number, and any LCA would need to have it. Stages is something that would depend upon the process or the product you are aiming for. Now, these are the basic 4 stages. Your LCA could have less than or more than it. It would depend upon the product life cycle that you're considering and the number of stages that your process has. So some of the principles of LCAs. It's always relative to a function unit, which means all the outputs that you're going to calculate would be in terms of some basic unit, which for an example could be CO2 equivalent. Whenever we are talking about global warming or climate change, it's in terms of CO2 equivalent. Any amounts of emission that we are releasing in the atmosphere are always in terms of CO2 equivalents. Or take, for example, the example of a light bulb. Possible function unit for comparing different types of light bulbs, which would be LCD, LEDs, or incandescent lamps, could be maybe 1 million lumen hours. Or if you're talking about transportation, it could be 10,000 passenger kilometers. So if you are comparing different modes of transportation, or one mode of transportation having different capacities, the typical function unit could be X passenger hours, or say 10,000 passenger hours. So that would give you the capability of comparing a car, maybe which can hold 10 passengers and it's riding for 1,000 kilometers, as compared to a bus which might hold 100 passengers and traveling over 100 kilometers. So we are quantifying both the number of passengers and number of kilometers. Same in the above function unit for the light bulb, 1 million lumen hours, which means it could consider a light bulb which is running for 1,000 hours and having an energy capacity or energy output of 1,000 lumens. Or it could also be comparable to a light bulb which is running for just 100 hours and the output is 10,000 lumens. And again, like only environmental aspects are addressed, as we've already discussed, and the whole process is iterative. We go forward and back till we are able to come to a mutual consensus that the LCA that we have done makes sense. So now we'll discuss all the 4 phases of LCA in detail. The first one is goal and scope. So in goal, or when we are defining the goal, we normally start with LCA with a goal statement, which would include the intended use, the reason why you're doing the study, the audience for which it is intended. So the LCA could just be intended to be done for a particular factory or a particular private firm. So it needs to be mentioned. If the audience is the government or any like ministry, it needs to be mentioned. If the aim is a broader audience like anyone, it needs to be mentioned. Whether it's comparative or whether you're doing a standalone study, that needs to be defined. Could it be disclosed to public or confidential is again something you need to define. And in scope, we define certain things like what are the different products we are trying to analyze. What would be the function unit? What would be the system boundary? What would be the allocation, impact categories? So we'll discuss all those things in the future slides. So these are something that we write down before we start an LCA. A typical example for a goal statement could be like this. It needs to have an introduction. It says the goal was to generate qualitative environmental profile of a management system for all the used oil generated in California. And then the reason for carrying out. Why do you want to carry out? Was it like funded by some agency or you're doing it on your own? What would be the intended use? Do I need to provide suggestions to the legislator as it is says? Or do I need to publish the data or whatever the use is? What is the intended audience? Like in this case, the intended audience will be all industries that are involved and affected by the management of used oil generated in California. And is this public or like confidential LCA that you're carrying out? So any good LCA should carry around like an extensive goal statement which clarifies all these aspects which we have discussed. Then it should have a function unit as well. A good functional unit should be a combination of three factors. It should give you the quantity, the quality, and the duration. So I'll repeat it again. A good functional unit should be composed of these three things. It should highlight the quantity, the quality, and duration. Like take the example of CO2 equivalence or global warming potential. It will give you so and so units of CO2 equivalents. So 50 CO2 equivalent. So the term 50 is basically referring to the quality. Quality means it's equivalent to CO2. How many, the global warming would be caused by not just CO2, but a lot of gases like methane, SOx, or CFCs. All those would have an equivalent to CO2. So we are making that equivalent to CO2, and that's where the quality is coming in. And this CO2 quality, when we are doing this, this could be over a duration of 25 years, 100 years, or 500 years. The most common assumption is 100 years, and that is where the duration is coming in. So what we are quantifying is 50 CO2 equivalent over a duration of 100 years. So that's why a good function unit, whatever it may be, should have the quality, quantity, and duration. We'll try to discuss this in more detail. So take for example, we are trying to compare three different types of lamps. It is an LED lamp, CFL, and incandescent lamp. So we suggest, or we decided to take a function unit which is 20 million lumen hours. Now these 20 million lumen hours could be achieved by different lamps in different proportions. Take in the case of LED lamp, maybe one LED lamp is good enough. Its voltage is very small, its lumen, the energy output is different, and its life is very large. Compare that with a CFL lamp. The energy input is more, the lumens are more, but the lifetime is less. Compare that with the most inefficient case, which is the incandescent lamp. The energy input is very high, the output is similar, and the lifetime is very less. So it has all the three features. It has the quantity, the quality. So the quantity is 20 million, the quality is lumens, and hours refers to times. How many years? So when we are comparing a lamp, a good function unit would be so and so lumen hours, which takes care of the quantity, quality, as well as the duration. Take for example, for the example of a transportation system. A good function unit would be so and so passengers kilometers. Now kilometers here is making in terms of like substituting for the duration, but bringing in another factor. Something similar could be the dormitory building. Like most of us are in colleges and we have the hostels. And if you need to compare the different hostels, a good perspective unit could be a house that could store 200 students in 1 year. If you want to compare the life cycle assessment of different hostels. Again, the choice of function unit would also be depend upon, like there would be a choice for you if we are going with the volume or the weight. Take for example of a shopping bag. So we could have a plastic bag, a paper bag, or a cloth bag. Now a plastic bag maybe has an area of 1 feet cube. It could hold 6 pounds of weight and it can be used one time and then you dispose it. In the second case, you have the paper bag. Again, similar kind of area. It might be able to hold more amount of weight because it's more sturdy, and it could be used maybe 3 times, and then it's good for disposal. The third case could be a cloth bag, which would have much more area and carrying capacity and could be used much more time. So again, we have the quantity, the quality in terms of weight, and as well as the duration. So when we are trying to compare a plastic bag with a paper bag to a cloth bag, a good function unit could be this much amount of weight for maybe this much amount of trips, or this volume of groceries in this much amount of trips. So the volume would give you the quality, and the amount would give you the quantity, and the trips would give you the duration aspect. Again, the system boundary. Now, a particular process could have many life stages. It would have the production of raw material, which will involve production and distribution, product manufacturing, distribution, use phase, and disposal. And so it would depend like what all product stages are we taking into account for that particular LCA. And there are standard terms that have been coined. The first one is gate to gate. You start with the factory gate and end at the gate. A typical example for the bioenergy systems would be the biomass arrives at the factory gate, you process it, produce maybe some biofuel, and at the end of the factory gate, you have the biofuel. So that's gate to gate. A cradle to gate would involve you grow the biomass yourself. You know how many fertilizers, how much machinery, what transportation has gone into the production of biomass, and then you process the biomass, pre-treat it, and produce bioenergy or biofuels, and you are just at the gate. So that was something that would call cradle to gate. Then there could be cradle to gate for the retailer and manufacturer. By manufacturer, it is available at the gate. For the retailer, it means it has now been available in the local market. So this would also involve the distribution and the retail network. And the most elaborate one is cradle to grave. You start with the growth of biomass, you focus on the conversion process, the distribution process, the use of that bioenergy, and final disposal and recycling. And is this the last thing? Not yet. Now what people are talking about is something cradle to cradle, which means you recycle the final products back to the growth of biomass. So there's also something called as cradle to cradle, where the final products are recycled back to displace some of the raw materials. So again, different life cycles that you are going to come across through your literature review or through your understanding of LCA would have different system boundaries. Some studies will only consider the gate to gate, and some elaborate studies would consider a cradle to gate. And if you are trying to compare the results of these LCAs, there would be vastly difference. The reason being there are so many aspects that people neglect. Again, bring out some critical aspects with the system boundaries. Now, people often neglect the upstream processes, and this has been specific to the case of biomass as well. The upstream processes, which is the transformation of the raw materials into useful form, is often neglected. And something that we need to take care here is the equipments that would be utilized. Might not be so prominent in India, but in the developed world, we have huge equipments which would be used for the production of these biofuels, and they would have their own energy consumption. Again, the fuel use that would go into these equipments as well as transportation. The land use. If the land that is available or has been made available for the growth of biomass being has been a conversion of agricultural land, forest land, because all that would have its own implications. Water use, waste flows. Some of the lead to a lot of waste. Where is that waste going? Is that waste sometimes causing more trouble? We need to quantify that as well. Then comes the second thing, the manufacturing phase. And the manufacturing phase is basically the conversion of the biomass into the biofuels or the bioenergy products or biochemicals, whatever you're aiming for. It would have consumption of energy. And one important thing that you need to take care is where is that energy coming from? Is that coming from gas or electric? Even if it's electric, in India we have different grids, and each grid is being fed by different sources of energy. The energy that we use in Uttarakhand is quite clean, but the energy used maybe in the areas of Bihar or Jharkhand is coming from all coal-based. So there might be a difference, or maybe if the CO2 emissions associated with electricity production is 0.7 per kilowatt hour or 0.7 CO2 equivalent per kilowatt hour in Uttarakhand, they might be around 1.4 in the states of Jharkhand and Bihar because the energy is coming from coal. The raw material use. These biomass processes would have a lot of raw materials that would be going in. If you're looking for thermochemical processes, it would have a lot of catalysts. If you're going for biochemical processes, again, enzymes are coming from. How are those enzymes being produced? Are they having an energy consumption? Then chemical use, equipment, and co-products. So this is another issue we'll discuss in the future slides. Then comes the use. We can maybe skip this. And finally, we are coming with the disposal, recycling, or the reuse. It depends upon us whether we want to dispose the final products, we want to recycle it, or we want to reuse it. And this would have emissions associated with it as well. Like if we are dumping the product, say we dump the landfill. If it's of biomass nature, it is going to release emissions into the atmosphere. Like you might have seen the landfill sites in India, and most of them are burning. The reason why they're burning is you have the methane that is escaping out of it. And when the methane escapes, a simple spark is good enough to cause its ignition. And that's why you see a lot of fire in the landfills. If incinerating it. Now this incineration would again have electricity requirement. Are you re-refining it or you're distilling it? So all these factors needs to be considered as well. What once the biofuels have been used or the bioenergy products have been utilized. And an important thing to consider here is sometimes you might come across net environmental benefits which are negative, say -5 kg CO2 equivalent of GWP. Does that mean you have sequestrated the CO2 from the atmosphere? Not really. It might sometimes say that, say you have a biomass product and you have recycled it. If you haven't recycled it, it would have caused 5 kg of CO2 equivalent emissions. So if you're recycling the product, you are avoiding those 5 kgs of CO2 equivalent. So in that case, it is saying -5 kgs. It doesn't mean that you have sequestrated those emissions. It just means you avoided that emissions. If we have gone by the business as usual scenarios or conventional scenarios, those emissions have been ended into the atmosphere and caused global warming and different emissions. And again, like we have the transportation, which is the elephant in the house. A lot of transportation is involved in the bioenergy processes, and that's why a lot of pre-processing is being gaining emphasis. People now want to have densification, pelletization, briquetting, as well as some even say like you pyrolyze the biomass, make bio oil, and then transport it. And a lot of considerations go into it. What are the modes of transportation? What is the fuel mode on which the vehicles are running? What is the distance over which you are transporting the fuels? What is the weight? And are they shipped with other products or are they shipped individually? So transportation is something that is very important in the case of biomass. And also is something related to transportation is the storage. So now biomass has this peculiar feature that when you store biomass, it would release gases. So there have been enough studies to state that if you store biomass for more than 1 month, it might cause enough emissions in terms of its degradation that might make the whole process environmentally unfriendly. So biomass, if it's stored, it is going to slowly degrade, and or sometime it might cause catch fire on its own as well. And this might cause a lot of emissions to the environment. So the storage of biomass coupled with transportation is one of the important aspects that needs to be taken care of when you are aiming to quantify the CO2 emissions associated with any bioenergy product. Okay, now coming to the life cycle inventories and life cycle inventory assessment. So by LCI, I mean life cycle inventory, which means quantifying all the inputs and the outputs, and life cycle inventory impact assessment. I mean what those emissions are going to cause. What is the dangers that are associated with those emissions? So let me take a small pause here and see if anyone has any question. I know I have been running at a fast pace. So in case anyone has any question, he or she can ask now, else we can continue. Okay, great. So let's continue. Okay. So now coming to the second phase of an LCA, which is called life cycle inventory, which means bringing in all the data for the inputs and outputs that might be required. So how do we get the data? Now there are different data types which are classified as primary data and secondary data. So primary data is something that you measure on your own. You have a process, you make the measurements on your own using different ways. Like if you have the exhaust gases, you can measure the composition of gases using gas chromatography, or you see the electricity consumption using electricity meters. So that is what I mean by primary data. Secondary data is something that is available through different databases. Like you are using coal in your plant. It might be some like anywhere. And then this coal is coming from a particular field. So that for that particular field, you will need the secondary data, what would be the emissions associated with the extraction and the energy production from that particular coal. Or even take the example of diesel or petrol that you might be using in the vehicles. So there are many databases that are available, and some of the good databases are the EcoInvent databases. We have the NREL US databases, which provide data specifically for the US. We have the Gabi databases. So if you're looking for India, there are two major sources for databases. One is the EcoInvent and the Gabi, which would have inventory specific to India. Rest, most of the databases that are available in public would be concentrated either on Europe or the US. Again, these data sources have been elaborated here. So the primary data would be the direct measurement or the communication with the companies or the agencies, which are your collaborators. Now, secondary data can also come from the journal publications. You study the journals which people have published and see what their assumptions have been, and you take the similar assumptions. We have different LCA databases. You have different softwares. Now, GREET is a good software as far as the transportation fuels are concerned. And then you also have the economic input-output LCA, which is an LCA combined with the economics. So even the databases for EIU LCA are freely available. And then you can also have the estimated data, which could be based upon either the primary or the secondary data. Coming to impact assessment, you know how many emissions you are causing at what product stage. Now, what do you do for that? You need to identify what impact those possible emissions can cause. Say, you have an emission of SO2. So what can potentially SO2 do? It can combine with the sulfur can combine with the water in the rain and cause acid rains. Now, these acid rains can acidify the lake. The lake, on being acidified, might lead to the death of the fishes or other marine life. And when the diversity in the lake is finished, it leads to a loss of biodiversity. A lot of fish have become endangered or extinct. So to repeat again, you have the sulfur that you release or SO2 that you release to the atmosphere. It could cause acid rain. This acid rain could probably acidify the lake. This acidified lake could lead to death of the fishes, and this death of fishes might lead to extinction of certain fishes, which might lead to loss of biodiversity. A similar example, take the CFC emissions. The CFCs, when released to the atmosphere, might lead to tropospheric ozone depletion. By OD, I mean ozone depletion, means there are holes in the ozone layer. That means the ozone layer is not there and the UV lights would come into the surface of the earth. This will lead to the UV exposure of the humans and then lead to problems like cancer. So this is how the whole chain works like. One emission could have an effect which could have an end effect. So when we are doing impact assessment, we can either focus on midpoints or endpoints. So the midpoint is an acidified lake or a stratospheric ozone depletion, which means this is the impact that have been caused. It is easier to quantify because it has much more scientific basis of it. We can quantify easily, like if these are the amount of emissions, this is the amount of acid rain which we can expect to get, or this is the level of decrease in pH of the lakes that we can get. But how much that decrease in pH of the lake is going to cause the loss of biodiversity is much less quantifiable. It might vary with the time, the place, and the circumstances. This is the effect for sure, but the relationship between these 2 points is not very quantifiable. The same goes with how much stratospheric ozone depletion is going to lead to how many cancers or how much decrease in the human health. Whereas the effect or the cause and effect relationship between the initial source and the midpoint is very well documented. So there is always a trade-off between midpoints and endpoints. So by midpoint, I mean these are certain effects which we know for sure are going to happen, and we can easily quantify them as well. But to a layman like me or like you, it makes much less sense. So what would an acidified lake sense to me? I don't like say the pH of the lake is 7 or 6, wouldn't make a difference to me. Or how much big hole is there in the ozone layer, doesn't make a difference to me. But if I say this hole in the ozone layer is going to decrease your life by 5 years, it makes sense to me. Oh, my life is going to reduce by 5 years. So this is where human health is coming into it. Or if I say this would lead to extinction of maybe 5 species of fish, this makes sense. So when I talk about endpoint, it makes sense to the common man, but the relationship between the source and the endpoint is less quantifiable. When I talk about the midpoint, it doesn't make much sense to the common man, but the relationship between the source and the midpoint is much more quantifiable. So when I talk about climate change, it's a midpoint indicator, kgs of CO2 equivalent. Doesn't make a difference to me. I don't know how many kgs would affect how much amount of global warming, but it is much more quantifiable. In the same sense, if I talk about this much amount of emissions are going to reduce my lifespan by 2 years, it makes sense to me. But again, I can't be really certain that it is going to be 2 years or 1 year or 3 years. It would change with a lot of assumptions. So that's why if you remember like the potential environmental impacts. So when we're talking about the endpoints, they think potential comes into picture. Again, the similar thing, you have the CFC emissions, which might cause to the ozone layer depletion. And then this could have end indicators like skin cancer, crop damage, cataracts, or it can even lead to materials like plastics. So these are the endpoints, and this is the midpoint. So it depends upon us whether we are aiming for categorizing the midpoints or endpoints. Again, it is the example of one of the methodologies for life cycle assessment, which is the most extensive one, and it has quantified many endpoints and midpoints. So if we have these all emissions coming from our process, it could be in terms of different gases as CO2, volatile oxide, phosphorus, SOx, NOx, CFCs, or different fertilizers. It could cause different types of midpoint impacts, which would involve the basic ones would be ozone depletion, climate change. Let me see where climate change or PM formulation, and the endpoint would be human health, ecosystems, and resource supply surplus cost. By human health is normally given in the unit DALY, which means disability adjusted life years. If these are the emissions that are taking place, how much years of my life are possibly reduced? So that's why it's called disability adjusted life years. How those emissions can possibly cause to a disability or reduce my life as a whole. Again, we have the ecosystems, which can be given in the number of years of the species lost. What is the lifespan of the species once those emissions are gone into the atmosphere? The other could be the cost in terms of the fossil fuels, minerals, and the water concentration. These are normally given in terms of what are the capital amount of those resources that are lost. And these endpoints can again be clubbed into a single indicator, as has been seen here. So the emissions that we have can be quantified into either midpoints, which are very easy to quantify, but again, doesn't make much sense to the policymakers or the layman, or it could be quantified as endpoints, which makes much more sense, but the quantification or the relationship between them is not very well developed. So again, now how do we calculate this midpoints? So we'll try to understand this with the help of example. Say I take the category of climate change or global warming potential. What does it try to quantify? It's quantifying the emissions of greenhouse gases, which is normally the bucket of six main gases, but it now has a lot of more gases as well. What is the characterization model? It is developed by the IPCC, which is the Intergovernmental Panel for Climate Change. What is the indicator? It's the radiative forcing over a time period of 100 years. And the unit is kg CO2 equivalent. So what do I mean by it? I normally refer to it by GWP 100. 100 means the number of years, and it's given as CO2 equivalent. So if I am emitting 1 kg of CO2, which means 1 kg of CO2. If I am emitting 1 kg of methane, that would be equivalent to 21 kgs of CO2. Now that number has changed and it's around 25 or 28. If I am at CFC 11, 1 kg of CFC 11, it's equivalent to 4,000 kgs of CO2 equivalent. And it can go, if I am talking about sulfur hexafluoride, 1 kg of sulfur hexafluoride is equal to roughly 24,000 kgs of CO2. So it means if I release 1 kg of sulfur hexafluoride into atmosphere, it's equal to releasing 24,000 kgs of CO2 into the atmosphere. So all of them, we are normalizing in terms of CO2 equivalent. So take, for the example, let's take this process, which has the following emissions. It has 20 kgs of CO2 going into the atmosphere, 2 kgs of methane, 5 kgs of CFC is 11, 2 kgs of NO2, and 1 kg of SO2. Now, all these gases would lead to one or more impact categories. Now, take for the example climate change or global warming. This would be induced by CFC 11 and CO2, as well as methane. Take for example the ozone depletion. This would mainly be caused by the CFC 11. Fine. The photochemical oxidation formation. This would be coming from methane as well as NO2. Then we have acidification, which would come from NO2 and SO2. Maybe so we have the different emissions which could come from different places in the lifestyle of a product. So these are the different emissions, and these are the possible impact categories which they could have. And then the characterization factors would be global warming potential, ozone depletion, photochemical smog, and acidification potential. Now let us try to quantify the effect of these. This is a type of matrix that you would be required to form. On the left-hand side, you have all the substances, the names of all the emissions, and these emissions could be any of the product stages. It could be either through the growth of or like say growth of biomass, or the production phase, the transportation phase, the conversion phase, the disposal phase, or the use phase. And this is a total amount that has been released into the atmosphere. Now, the first thing that we need to put is the like the characterization factors, which would be 1 for CO2, 21 for methane, and 4000 for CFC11. So these are all coming from here: 1, 21, 4000. And similarly, the ozone depletion is just caused by CFC11, so we have just have 1 here. For the photochemical oxidation, it is coming from 2 sources, which is methane and NO2. And the unit for that is kg ethylene equivalent. We don't have any emissions of ethylene, so we don't have 1 anywhere. We just have the conversion factors. The same goes for acidification potential. It is caused by NO2 and SO2. Since it's in kgs of SO2 equivalent, we have 1 in front of SO2, and then the conversion factor in front of NO2. But
sir,
how do you quantify? Yeah.
These conversion factors from ethylene to methane and NO2, are they given in literature, or we need to calculate based on molecular weight?
No, they are given in literature. So they are quantifiable. They are quantified. Say like the GWP is normally reported by IPCCs, and so is the ozone depletion. So these are the factors which are applicable to all the countries equally. But other factors like acidification or photochemical oxidation formation, it would have a lot of other factors, and it has certain geographical applications. So certain factors might be applicable to Europe, but might not be applicable to India. So these have to be seen in terms of geography as well as the time period.
Okay.
So there are different publications available, which factors are available in which place. So you need to adopt those. As far as the GWP and ODPs are concerned, these are quite universal. You can adopt them straight away. But other factors, you need to see that they're applicable to your particular geography.
Okay.
So going further, now we have 20 kgs of CO2, which have an impact of 1, 2 kgs of methane having an impact of 21, and 0.05 kgs of CFC11 having an impact of 4000. So we need to multiply the amount with the possible impact, which is 20 into 1, 2 into 21, and 0.005 into 4000, and then add them. And adding them will give me the total impact from all the gases, which would lead to global warming potential. Again, you can see here, it's not just the absolute amount, but also the conversion factor that is playing a major role. Say, both from CFC11 and CO2, we are getting a value of 20 kgs of CO2 equivalent. And if you see the absolute amount, the CO2 is just 20 kgs, and the CFC11 is just 0.005 kgs, 3 orders of magnitude less, but the impact is similar. So a gas might, or an emission could be released in a very minute amount, but could have a very big impact. So this is something that you need to keep in your mind. So we have this total of 82 here, and something similar can be done for all the others. Like the ODP is just 0.05 into 1, we have 0.05, and we multiply these factors, we get these results. And the similar thing could be acidification potential as well. So LCA LCA results in like maybe in a short span could be understood with the help of this slide. So these are the emissions through different life stages. We have the different impact categories which we want to consider. We multiply that with the characterization factors, and we could have the final results. The GWP potential is 82 kgs of CO2 equivalent. The ozone depletion potential is 0.005 kgs of CFC11 equivalent. The photochemical oxidation formation is 0.068 ethylene equivalent, and the acidification potential is 2.4 kgs of SO2 equivalent. So this is the LCA in a crux, how the calculations are done. And in reality, it would have a huge matrices, maybe 50 by 50, and some amount of matrix algebra, like multiplication of matrices, how you calculate these factors. And the last phase is interpretation. You try to interpret the results based upon like what assumptions you have taken, and try to draw out the conclusions and the recommendations. And again, these conclusions, recommendations should be based upon the goal and the scope. You should never exceed the initial goal and scope that you have stated. And the LCS should also reflect various uncertainties. So it's always recommended that you carry out an uncertainty analysis that will give you an idea which are the particular product stages which are the most uncertain to us. And this will give you the effect where the possible hotspots which need maximum attention. So there might be certain process stages where like a small change in the process configuration could lead to a lot of emissions. So you need to highlight those. Again, there are a few limitations to an LCA. Like it's not a complete assessment of all environmental issues. No matter how many impact categories, midpoint or endpoints you choose, you can't take care of all the environmental issues. There would always be gaps. And that's why you have this goal and scope. And LCA can not include every single process and capture every single input or output. That's not just humanly possible. And that's why you have the concept of system boundaries, data gaps, and cutoff criteria. So you need to define the system boundary very clearly so that the persons who are trying to understand your calculations know what are the assumptions you have taken. Now the data would have uncertainties. Although it's recommended that you work on primary data, but invariably you have to adopt secondary data, and this secondary data would have its uncertainties. A data that is there for the US might not be applicable to all the calculations in India or Europe, and vice versa. And again, these characterization models are far from perfect. Like certain models, like the global ones, which are there for the global warming and ozone depletion potential, are better, but other midpoints or endpoints are geography specific and have a lot of local assumptions built into it, which needs to be understood and modified if needed. And again, like the uncertainty analysis being done, but still there's a lot of scope for that in the future. So with that, let me bring in some of the issues of LCA that needs to be considered when we are doing the LCA of a bioenergy system. So now this is this I have taken from a review by Anup Singh, and he brought out what are the mostly covered parts of an LCA, the less covered and the least covered. So most of the LCAs, when talking about bioenergy systems, would talk about these things: bioenergy transport, conversion, distribution, and use. What are the direct resources coming in, the direct emissions going out? Very few would talk about the production of biomass, which is the direct agriculture land use. And even less would talk about what that land use has. So that land use could have indirect emissions as well. It could change the people have been doing agriculture, or change dietary habits, or it could have, again, its energy cost, trade policies. So many of these things are very difficult to quantify, and that's why very less LCA studies cover them. But nonetheless, it is important to keep this in your mind, that some of these things, like the change in the land pattern or the land use from your biomass growth, could have major implications as well. Again, this brings me to types of LCAs, which people normally don't talk about, but it's important to understand. Now, there are two types of LCAs. One is attributional and the other is consequential. By attributional, I mean, say I have a biorefinery. I know what my inputs are, what my outputs are, and I just quantify that for 1 kg of this biofuel produced, these are the emissions I'm causing. So that is attributional, simple. The other was is consequential. What are going to be the consequences of the product? Say now I want to bring up a biorefinery in the future. If I bring in a biorefinery in the future and I'm producing bio-oil, which means if I have another crude-based biorefinery in the vicinity, that is not going to function in its full capacity. If that is not going to work in its full capacity, which means it's not going to work at the full efficiency. If it's not working in the most efficient manner, the crude that is getting refined has an increased emissions associated with it. So indirectly, if I'm going for a greener fuel, I might cause emissions in a fossil fuel-used biorefinery. And this is something which is a consequence. That's why I call it as a consequential LCA. And this whole thing, which I'm talking about here, is a part of consequential LCA. So we need to be very sure like whether we are working for an attributional or a consequential LCA. Attributional means I am not worried about how the world is functioning. It was functioning before the process came in and it will function after the process comes in. That's not one of my concerns. I'm just concerned about my bioprocess. This is the input going in, this is the output going in, and this is the emission associated. In consequential LCA, I am worried about it. What are going to be the consequences? If I'm going to grow biomass on this particular amount of land, so the original plantation has to be shifted elsewhere. If the plantation is shifted elsewhere, is it going to cause more emissions? So that is where consequential LCA comes into being. And then it is again change oriented. It has marginal data that is being used, like the state of the art or the best data is being used. And then I won't go into the other things, but it's important to understand the difference between the two kinds of LCA. The other thing is the land use change, which I believe we have already discussed in detail. I won't go into this. Then comes water use. So this is an interesting slide which gives in the liters per megawatt hour of energy consumed. So if I'm talking about petroleum extraction or oil refining, they would consume around like 50 to 150 kgs of or liters of water per megawatt hour of energy produced. If I go for oil shale, it would have much more water requirement because water needs to be pumped at supercritical pressures into these shale mines, and it is even more for coal because coal plants have a lot amount of water requirement. But if I talk about biofuels like ethanol or biodiesel production, it is many times greater than the conventional energy or production processes. And this is why LCA becomes important. So some of the features like the use of water could be many times higher as when we are comparing this biomass energy processes. Transportation. Now, transportation wouldn't have similar emissions. They are different modes of transportation and they would change with different places. Like even today, if you see, people are saying that if you bring electric vehicles into India, the emissions are more than the conventional vehicles. A simple reason for that is most of our energy is still coming from coal-based electricity. The only thing that we are doing by bringing in electric vehicles is shifting the emissions from the cities to the coal power plants. It might improve, it should improve in the future. This is what I would say, as we are going towards renewable energy sources like more solar comes in or more wind comes in or more biomass would come in. But as of now, it is having more emissions. And this is what this slide says. Like the biomass, say pellets, or if you're transporting over different continents, would have very different emissions. Like the change in emissions could be almost 3 times if you are shipping by ship or a train, or in different places as well. The transportation of biomass is something that needs a lot of attention. Then comes in the aspect of multiple products. Now, rarely you would see that any biomass process is just giving you one product. It would have a plenty of products, and that's where the concept of biorefinery is coming in. So that biorefinery means there are multiple products. So let's take an example. Say I have a unit process which is giving me 20 kgs of a product A and 80 kgs of a product B, and the emissions is 1 kg, the total process. So one way I can allocate this emission is on the basis of bars. I know I have total 100 kgs and 80 kgs is product A and 20 kgs is product A and 80 kgs is product B. So the simplest way of this allocation on mass basis would be, I divide this process into 2 processes. The first process gives me 20 kgs of product A and the emission associated with this 0.2 kgs. The other process gives me 80 kgs of product and it has emissions of 0.8 kgs. Simple, makes sense, nothing to worry about. But what about if we consider the economic value? Say I have the unit process and it gives me again 20 kgs and 80 kgs, but the value of that product A is $900 and the value of product B, 80 kgs of product B, the total value I'm talking about is $100. How do I allocate? The other type of allocation could be basis of economics. In that, again, I divide the products or the process into 2 stages. The first one gives me 20 kgs of products. The value is $900. The total value being $1,000. So it has 90% of the emissions, which is 0.9 kgs. The other product is 80 kgs, but has a very low economic value, maybe just $100, and the emission associated is just 1 kg. So this is one of the major dilemmas that any LCA practitioner will face. How do you allocate the emissions? So if you consider these two things, both are good, both are fine, both are like right in their own spheres. But if you see the emissions, it's just reversed. In the first allocation, there is hardly any emissions for product A, and all the emissions are going to product B. If I do my economic evaluation, all the emissions are going to product A, and B is appearing to be fairly green. So these are some of the issues that you would come across when you are doing an LCA. And so this was just to give you a preview. And then comes the case of biogenic LCA, biogenic carbon. Now it says that say I'm producing biofuel. So, but this biofuel would replace a diesel or a gasoline, conventional diesel or gasoline in the vehicle, and I'm going to use that fuel. It's going to cause CO2, and that is going to the atmosphere. So people say, how come the biofuels are carbon neutral? Because anyway you're burning those fuel, and the CO2 is anyway going into the atmosphere. So the way bioenergy is carbon neutral is that the CO2 that is going into the atmosphere after the consumption of those fuels is going to be used in the growth of new biomass. So a typical cycle for a biomass would be 20 to 30 years. So I can expect the CO2 that I release today by the consumption of biofuel would be taken in by the growth of new biomass in the next 20 to 30 years. The shelf life of this CO2 is pretty small. The same can be said for fossil fuels. The fossil fuels are the same. The CO2 from the atmosphere is getting stored in the cores of the earth or in the depths of the ocean, but that takes millions of years. The shelf life is very large. So when we are using biofuels or conventional fossil fuels, the cycle is almost similar. It's just the shelf life of the CO2 that is getting reduced. So, and any biomass process is neutral only to the extent the biomass is being grown again. If you are just cutting trees, producing fuels and consuming them, the biomass process is not carbon neutral. It is even causing more emission than you would have caused when you would have utilized a conventional fossil fuel. So the process is environment friendly or close to carbon neutral only in case when you are growing that biomass again. So take for an example. So this is what a conventional process would be. You have the biomass, there would be natural fire, and the CO2 goes into the atmosphere. And when the biomass grows again in that place, the cycle is completed. So this process is carbon neutral. When we are going for a bioenergy system, we have the biomass. The conversion takes place with the help of some fossil energies. All the biomass processes that we come across nowadays would have somewhere or other fossil energy coming in, if not in the main process, in the transportation. And then the emissions are both this biogenic as well as the geologic carbon, which is coming from this fossil fuel. And the one that is returned is only the biogenic CO2. So if someone says you that any biomass process is carbon neutral, they are lying, because they can't be neutral. It could have very minimal CO2 emission, which is coming from just this fossil fuels, but it is very rare or almost impossible to get a biomass process which is totally carbon neutral, because there would be energy that is going into it. Compare that to the fossil fuel. You have the crude oil, you have the fossil fuel coming in, and you have the atmospheric emission. So this is a conventional fuel, and that doesn't get returned. So that case is not there. Even if you're using biomass in here, it's more or less the same if we are not having this return of the CO2 that is happening. So I had two case studies which I can discuss or I cannot based upon the discussion you want to have. So I believe I have I just have 15 minutes left. So let me see if you have any questions. If not, we can have a discussion on the case study. Okay, so no question means either you guys have understood everything or nothing. So please, like, yeah, anyone? Okay, it's Tonal. Okay, maybe I'll continue with a case study that would take another 10 minutes or so.
We have 15 minutes.
Yeah. So I can continue with the case study. This is something again coming from my PhD, and I will also try to discuss something similar in tomorrow's class as well. So what I was trying to do is produce ammonia from biomass, and that was through the gasification process. I wouldn't go into the details, and what I did was I chose three different biomasses in three different places around the world, which was straw in India. We have a lot of straw. We chose bagasse in Brazil. Brazil is a country which has huge sugarcane plantations and a lot of bagasse. And the final thing was eucalyptus in Australia. Now, Australia has huge amount of land, hardly any population, and that land could be used for production of huge amount of trees. And you can see these three biomasses are coming from three different categories. Now, eucalyptus is an energy crop that can be grown on purpose. Straw is a farm waste available in farm, plenty and scattered. And bagasse is an industrial waste, which is available outside the industry but has many side uses as well. Three different types of supply chains, three different types of characteristics. And the aim was to produce ammonia, a same chemical, from all of them. And this is a flow sheet that I adopted. So it was basically cultivation of biomass, transportation, we gasify biomass, and we get a syngas which is rich in hydrogen and carbon monoxide. We have a series of chemical treatment that goes into it and an ammonia loop, and finally we get the ammonia product. I won't go into the process details as of now. And then I did an LC of the whole thing. So the LC would involve the cultivation, the transportation, the electricity that is going in, the utilities I have, the catalyst for like a gasifier would normally involve a bed material like olivine, charcoal, and the output would again be particulate matter, ash. So these are different filters that is going on. We have electricity for consumption. We had steam requirements, adsorbents going into the PSAs, catalysts. So these are the inputs that I took, and I could quantify the CO2 emissions from different parts of the plant. So if I was to put it in a plant, I could say some amount of CO2 is getting absorbed while the growth of biomass. Then all the processes would more or less release the CO2. The transportation would have its own emissions. The gasification would have emissions. Now people say that gasification is a carbon neutral process. No, it has emissions. Reforming would have emissions. Reforming is done because the syngas has around 10% of methane, and what I needed was hydrogen. So we need to reform the syngas. I need electricity for compressing the syngas, and that is coming from grid electricity. We have a PSA here which removes all the CO2, and this CO2 is getting removed in here. So that's why a lot of emissions are coming in here. So this is a way I can quantify the emissions that are coming from different product stages. And then we can also quantify how the same process behaves in different countries. Now this is the same process, biomass to ammonia, but three different biomass feedstocks, which is wood in Australia, straw in India, and bagasse in Brazil. The GWP potential is vastly different. Some of the reasons: electricity, you can say, is the largest contributor to GWP on all the three cases. In Australia, the electricity is produced from coal, but the coal is very clean. Even we import coal from Australia when it comes to iron and steel industry. In India, we use the dirty coal that is available in our mines, and so the emissions are very high. Brazil has electricity coming from hydropower. Electricity consumption is very low. Take the example of biomass cultivation. In Australia, it's somewhere in between or somewhere similar to Brazil. In India, very high. The reason: we are using much more amount of fertilizers and pesticides than it is needed in our crop production or straw production. And this invariably adds to the LCA of straw as well. Now, straw is an end product which doesn't have much value. So if you see the say allocation, even in that it would not have much value, but you can see there are so much emissions associated with the cultivation of straw. So the same process would have very different emissions when you're diffusing different biomasses in different countries. So this is one takeaway that I want to bring in. The other thing is, take for example of ozone depletion. Again, the same three biomasses leading to the same process, which is ammonia production. Now, there could be a wide amount of difference in the total impact, but also where this impact is coming from. Like, take for example, the impact in Australia is mainly coming from transportation, which is huge. In India, it is also contributed by electricity, which is almost absent in Australia. Also in biomass cultivation, huge. Take the example of Brazil, it's only most of it is coming from electricity, and some amount of it is coming from the reformer fuel as well. So same impact category, same processes, we could have very different emissions, and the source of those emissions could be very different. So I can't say that if this process is good for India or for the US, this would be good in Australia or Europe as well. We need to do a separate LCA. We just can't draw parallels. Then in certain ways, I'm here comparing the conventional production of ammonia from natural gas as compared to those three processes, wood to ammonia, straw to ammonia, and bagasse to ammonia. We can see when we are using this process in Australia or Brazil, it's quite fine. As far as India comes, the eutrophication is almost double. Again, the reason is a huge amount of use of pesticides and insecticides, which end up in the water bodies, increase the nutrient content, and these nutrient content increase the algae growth. This algae growth leads to depletion of species. Something similar for the marine eutrophication. It could be very high for India. Then comes agricultural land occupation. This is the conventional process. The only land I need is for the factory. I would hardly need any land for straw or bagasse because they're available just out of the field. But when I'm doing an energy plantation, I need a huge amount of land. So again, the same process, different biomasses, different places, the impact could be very different. So this is agricultural land application. And if I go for normalizing all of them and bringing them into a single score, I can see that I have some amount of saving. Even in the worst case, as in India, I still have some amount of saving. It is largest in the case of Brazil and somewhere in middle in the case of Australia. So this was a study done or shown to emphasize on the importance of LCA, that the same process could have very different impacts, which could be coming from different biomass. It could come from different supply chains, different characteristics, or the national factors like we have in India, like the electricity is coming from dirty coal-based power plants, or even a lot of use of pesticides and insecticides in the fields. So this is something that I would like to discuss tomorrow. Yeah, so maybe I can stop in here. And in case you guys have any questions, I would be happy to answer. Not only questions, even comments or like even corrections are welcome. If you feel that you have some comments on this or some suggestions, I would welcome those as well.
Hello. Hello.
Yeah.
Good afternoon, sir. Sir, actually, I just want to ask one question. Regarding how, sir, did you calculate the single factor value?
Okay, so there are normalization techniques that are available which you study, like you can just study the recipe methodology, and they will tell you that how you quantify these values into, like it's all this the division by a factor, which is available for different countries, and you just multiply by those factors and add them up, you'll get a single value.
So, sir, can we get these factors from the literature or from the different agencies?
Yeah. So so there are different people who have formed this impact categories or characterization methods. So there are certain methods that are specific to Europe, like recipe. There are certain methods which are specific to US, like Tracy. There are certain methods which are more global in nature, like Impact 2002 Plus or Impact World Plus. So you need to see which are the characterization factors which are applicable to your place of study, and they're available. And they would have publications to support them. And then there would be many publications who are taking information from those factors. So most of them are these companies, the LCA companies, or a collaboration or consortium of universities who publish this data. And it's available freely.
Freely. Okay. Thank you, sir.